Hey everyone, I'm Justin, and do you have the display? There we go. Okay, really right up here? Okay, cool. Okay. Good afternoon, everybody. I'm Justin, co-founder of Althea, and today I have a talk that's about Althea L1, but really the design decisions behind it. So for that, we're going to need to start with some context. So Althea is a DPIN project, decentralized physical infrastructure. Although we really predate that definition by several years, and I'm not really here to talk about Althea the application so much as the L1 that we have built to support it. And this is because I think it's a really interesting alternative interpretation of the scaling problems that sort of dominate blockchain design discussions. And what I found really interesting as we went through this process of designing an L1 for Althea is that the choices that we made and the options that we selected were completely different from the normal, more DeFi-focused blockchain design discussions and decisions. So this led me to want to sort of present all of these differences and really talk about what does DPIN need in a scaling platform as a sort of contrarian, or I guess not really contrarian, but an alternative to the sort of L2s, L3s, ZK discussions around DeFi scaling. Now, I should get out of the way some context. So Althea is a protocol that allows devices to buy and sell bandwidth from each other. So for the super short elevator pitch on that, just imagine that your cell phone could buy bandwidth from any cell tower, not just one of the three main providers, but any cell tower, anyone set up, as a metaphorical equivalent of just kind of handing them a quarter as you walk by in order to buy some data. And so, yeah, this is a microtransactions application. It's really about creating a market for bandwidth. And we have been working on this for 6 or 7 years now, depending on how you count. And we are selling, we are an ISP to thousands of homes in 15 states and several countries. And we have real customers buying bandwidth using this system from for example, a fire station to just regular people who are not familiar with crypto at all using this as an application. So now we're starting to think of, well, not starting, now we're implementing, what does it take to do this at scale, to have a bandwidth market like this running for everyone in America or everyone in the world? And how do we make sure that it scales and everything works out? So without further ado, let's get started and sort of jump right into the technical decisions. So first of all, how much block space do you really need anyways? And I think this is one of the things that is this is one of the discussions that's sort of dominated by more block space better arguments. And that may be reasonably true in the case of DeFi and sort of financial applications. More block space creates induced demand. So the lower your gas costs, the more transactions you're going to get to arbitrage all the pools and to arbitrage between different protocols. And it just goes on forever, really. But that's not true when you are buying and selling what is, I like to think of bandwidth as a physical good because it's transmitted through the air. It's really not so different than a candy bar. Once you have downloaded some data, the sender cannot take it back, and they still want to get paid for it. And the interesting thing about microtransactions applications in this sort of context is that you think, well, okay, you want to send transactions as often as possible, right? That's not really the case. In fact, the frequency with which you want to send transactions is bounded by the latency of the system that is accepting the transactions, so finality speed. And that's an unintuitive answer until you start thinking about trying to write the code that actually does this stuff and start trying to think about writing it in a way that is reliable enough that your phone is not constantly ringing. And to do that, you really need to worry about what transactions are in flight. what is final, what is not final, what could be reverted, what could be changed, what if somebody unplugs the device, what if somebody reboots the device, what if somebody reboots the receiving device, what if the receiving device has corrupt memory because it doesn't have ECC. All of these things are things you really need to worry about. So being sure that you have sent your payment, that it has been finalized on the blockchain, and that the receiving node understands that it has been paid are really your constraining factors. So what this means is that you don't want to settle every, 1 second, 5 seconds. You really want to settle every couple of cents, maybe 1 cent, 5 cent, anything more than that, and your tracking logic starts to go wonky. Because so let's say you have a centralized shared sequencer that gives you an inclusion proof. This is the fastest you can possibly know that your transaction has been accepted. How fast is it? How fast is it really in the worst case? And the answer to that is probably about 1 to 2 seconds. So that's not actually that much better than the finality time you can get so we ended up selecting Tendermint consensus on a Cosmos base, and finality times sit around, somewhere between 4 and 8 seconds. So as a single centralized sequencer acts as a single point of failure in the sense that, well, point of failure, point of liveness failure, I should say. There's safety failures as well. But you're not getting a big benefit from it. You can have a decentralized validator set, and ultimately, your biggest constraint about how many transactions you want to send doesn't change. This is a really interesting and unintuitive conclusion, and it's kind of the sort of thing that this whole talk is about, is what we've learned building Althea and running a DPIN application, and how that influences what you actually want to build. Yeah, so anyways, the ultimate conclusion for this is that you don't really need an enormous amount of block space. In terms of block space, everybody's going to be settling, let's say everybody was streaming 4K video continuously, they were all paying some absurd price per bit, just to generate more transactions. You're talking about maybe tens of thousands, tens of thousands per minute, to a couple thousand per second to settle all the bandwidth in the United States. And that's if everybody was watching 4K Super Bowl same time, et cetera, et cetera. So you don't need to start to get into really crazy scaling solutions or ZK proofs or lots of multiple shards. You can reasonably do this with a simple validator set and well-optimized code. Even more interesting than that, and on the same subject, is that scaling for DeFi is actually a much harder problem, which you may have already guessed listening to just the first couple of minutes of this presentation. When you're doing transactions for real-world value, you can parallelize them really easily. You're not talking about reducing the composability of a programming environment like the EVM that is fundamentally about, well, so the value of the EVM is fundamentally about composability. That composability fundamentally requires that you serially execute each transaction, and means that you can't really take advantage of parallel processing on an individual validator very easily. Whereas if you're processing a bunch of just straight up hard-coded A sends money to B transactions, these can all settle at the end of the block and be processed in parallel, and then you wrap up the block and do the signing in one thread at the end. So this means that for Althea L1, we've gone with a hybrid platform where we have both a base layer that allows us to send just bandwidth transactions as a special type that we can process vastly more efficiently, and then an integrated EVM that is useful for DeFi applications that want to be close to the actual bandwidth sales, but at a really high price, because we're not really optimizing. Well, really high price is relative, but we're not really optimizing for enormous EVM throughput. We're optimizing for enormous bandwidth transaction throughput. And once again, I think that this is interesting from the perspective of how much what you were trying to do constrains your scaling concerns. And this brings us to the last point, that while figuring out a form of parallelism and increasing the speed of serialized execution is the hardest problem for EVM chains, the hardest problem for a chain that hopes to be a settlement layer for real-world exchange, whether that be candy bars, bandwidth, pretty much anything physical that has to change hands, you need two things more than anything else. You need some form of instant finality to get more, to actually get the transaction throughput there and to simplify your applications. And you also need a way to handle the RPC problem, which is actually really, really hard. Because when you are dealing with DeFi, it's relatively reasonable to have a very high full node, or I should put it this way, RPC node to user ratio. Because users are not transacting all the time and do not need to be observing the blockchain state constantly. They, you know, there are arbitrage bots and such, but they can pay for their own infrastructure. You don't have a router that needs to know when it's been paid, a point of sale terminal that needs to be always on and watching for payments. You don't have essentially an enormous query load that is the real bottleneck when dealing with real-time payments, because they have to remain real-time. So obviously, no matter how many queries you run, the validators are going to keep producing blocks at about the same rate. You're not going to knock them down. But if the users cannot query and know that their transactions are finalized, we're back to the first point. We don't have fast enough finality. So this is why I think the light client space is really underappreciated, and that the current, I think the current concepts behind client diversity in Ethereum and in other blockchains are insufficiently advanced. Why do we have only one type of client that's a full client and an archive node? And it does only those two things. Because we really need more effective light clients that start to eliminate these RPC problems, start to run in a web browser, and give us query capability that is really efficient and useful. Now, unfortunately, Ethereum has designed itself into a corner here with its own, with its non-final, sorry, I'll put it this way. The delayed finality in ETH2 consensus fundamentally makes it extremely difficult to make a lightweight light client like this, because the proofs that are needed to do that don't really exist in a practical way. This is useful for Ethereum because it provides additional resiliency in that it's not final, but because there is no finality, you have a data availability problem, and the data availability problem cannot be solved with a quick proof. So that is a bundle of words in there. But long story short, for our application, for DePIN applications, we need to be able to bootstrap a light client that can effectively query other nodes for blocks in a, couple hundred megabytes of RAM at most. So the, okay, sorry, I'm not going to go on a detour about home Wi-Fi router hardware and how much RAM they have, but that's an entirely different lecture, and is something that has been a really fun problem, interesting to work with. But anyways, compared to a home Wi-Fi router, a Chrome tab is practically roomy in terms of resources. So yeah, so particularly we chose Tendermint as our base. Tendermint provides sacrifices, liveness for instant finality, which we needed before, and we also need now to make effective light clients. And these effective light clients are critically important to maintain the query load when you have, let's say, 300 million households, 2-3 devices each. All of them are looking at the chain pretty much continuously. That's not practical to do any other way. You need an efficient light client, or everybody's going to be having the same terrible experience that blockchain natives have when you're trying to use a chain and the RPCs are heavily overloaded or not responding, or when you have to pay out the nose to Infura to get yourself something stable and sort of avoid that problem. Now, this brings us to the last one, and that is that data availability. I think this problem is sort of interesting, mainly because the way that it's being approached right now is as a financialization problem. And I don't really think it's a financialization problem at all. And in order to, that's because I'm coming at it from a hardware first perspective. And as somebody who spends a lot of time dealing with physical hardware, that's kind of where my mind is. But in terms of storage, the storage is dirt cheap. You can buy enough storage for a ETH full node, considered to be like a really heavy blockchain, for $64. And the immediate response from anybody who has ever tried to run an Ethereum full node will tell me that that storage isn't fast enough. And that's a problem with the program, not a problem with the fundamental requirements of what you need to do. So, the amount of data you need to store is the same. The fact that you need really fast storage is an artifact of, once again, the expectation that there's only one type of chain client, a combined archive full node. And I think that needs to change with more intelligent light clients. And Ethereum is, like I said, it has some problems with that. You're not going to fit an ETH2 light client in a browser, but you can definitely fit an ETH2 light client in a lot smaller footprint than you have right now if you came at it from that sort of low processing envelope perspective. But right now, the focus on client diversity is just having diverse clients that all do the same thing, and not a ultra lightweight client that is prepared to store only part of the blockchain at a time. So anyways, for our purposes, for Althea L1 purposes, if we're talking about many millions of home Wi-Fi routers, point-of-sale terminals, people's phones interacting as sort of medium-weight light clients, where you have a few hundred megabytes of RAM and maybe a gig or two of storage, data availability becomes a logistics problem. You just have to have each node store a random distributed sampling of all the blocks and respond to queries for them. And if you have a sufficient number of nodes, then data availability ceases to be a problem. The issue, of course, is having a sufficient number of nodes, which ties back to why we need lighter clients, so that running nodes is far cheaper, and there are far more of them. It would also help if they didn't require such enormous amounts of maintenance, but that's part of the design requirements of building a lighter weight client. Okay, so hopefully I have not just all confused you all silly, and there are some intelligent questions to be had. Well, either way, there is, we have some merch over at table A5. Yeah, that includes free t-shirts, although I don't think for long. Yeah, I'll be happy to answer questions and talk about this after, since it looks like I'm going to run out of time in a minute anyways. Thank you, everybody.